Now, my name's David Alexander, and I sort of have been working on this, what we call the Space Frontiers lecture series. How many here were at the first one? And you came back, thank you. You know, one of the things that we all know, and I'm not going to take too long, but one of the things we all know about Houston is it's always been associated with space in one way or the other, at least for the last 50 years. And so what we're trying to do is bring that to Rice in a much more coordinated fashion. If you walk around Rice, you'll see most of the departments have something to do with either NASA or space in some way or other. Even in anthropology, I only found that out after our last lecture when a student contacted me. And as most of you know, there's a lot going on in this next year, year and a half, both with NASA and with Houston, and with Rice. We have our centennial next year. Hopefully you visited the centennial program. It's a series of events that will be happening over the course of 2012. This year there's lots of anniversaries. We've already had, our first lecture was on the 50th anniversary of President Kennedy's inauguration. April 12th sees the 50th anniversary of Yuri Gagarin's flight. September, I believe, was the inauguration of Johnson Space Center, in which Rice played a big role. And next year we will see the 50th anniversary of President Kennedy's To the Moon speech, which of course happened in our own stadium here. I actually talked to some people who were at that event, which is quite exciting. So the space, one of the things we started to get this awareness going, if you like, was to start the Space Frontiers lecture series. It's part of a larger initiative that we're trying to do. We're calling the Rice Space Initiative just now. We're developing a series of things like the Professional Science Masters program that some of you were at last night, and a few other things. And if you're interested in hearing more about that and maybe even participating, you can get to me through the Dean's Office of Pamela or Emily, and through Rice Space Institute. Pat Wright is here. One thing I forgot to do at the first lecture was thank the most important people. Not so important, but who provided the funds are, of course, Dean Carson. You can't recognize him because he's not wearing a shirt and tie, but he's down over there. Natural Sciences, and of course the Rice Space Institute, the director being Pat Wright here, who you may have seen on CNN today as essentially a Skype correspondent for the shuttle launch, which was successful today. But more important than these two, thank you. We're not here to take the thanks, are Pamela Jones and Emily Topp, who are in the Dean's office, who basically, there they are, sorry. These two guys have been, I mean, they do all the work, and they arrange for everything, they do a lot of the advertising, they put the posters up, they send out all the emails, and any success that the program's having is really down to these two people. The money's nice, but the work is more important, and that's these two, so thank you. Let's see. Tonight, I'm really pleased to have one of the significant leaders, not just in our field, but in a number of fields that are related to some of the things we do here at Rice. And what we're going to hear about tonight, this is the science talk, if you like. This is where the sun hits the earth and does some stuff to space. And I'll leave the details to our speaker. Before we go on to Lou, I want to point out our next speaker will be March 10th, so it's not a month away, it's actually sooner than that for the students here. It'll be pretty soon after spring break. But that talk will be Franklin Chan-Diaz. He's a career astronaut who now has his own propulsion company. He's developing a plasma engine that, if it works and if it's fun, he will take us to Mars in 30 days. There are some other issues about getting to Mars, but I think it'll be a very interesting talk. But it's March 10th, it's not near the end of March.
Somebody's fingers
introducing our speaker, I've already taken enough time.
Somebody's fingers in front of the projector.
Tom, you need to lean
forever, so I'm going to just forgive me, you can look at his bio online at spacefrontiers.rice.edu. I'm only going to pick a couple of the highlights. I personally know of his work through a number of different reasons. He's also an editor whose job is to give me some grief for a different reason, of the Space Weather Quarterly, and we have a bunch of these that are available for you to take with you if you don't have one already. That's one of his many jobs that he does really, really well. Dr. Lanzerottti is a distinguished research professor of physics in the Center of Solar-Terrestrial Research at the New Jersey Institute of Technology. His BS was in, his bachelor's was in engineering physics from the University of Illinois. And he got his PhD degree in physics from Harvard. And then he went to Bell Labs. For some of you who know, Bell Labs are the important role in the history of science in this country. And he was there, I guess, from 1965. Up until 2002, when he retired from Bell Labs and moved to NGIT. He's a member of the National Academy of Engineering and a member of the National Science Board, which governs the workings of the National Science Foundation, and that board also advises the President of Congress on science and engineering issues. He's a two-time recipient of the NASA Distinguished Public Service Medal, recipient of the Antarctic Service Medal of the United States, recipient of the William Norberg Medal from Coast Guard, which is the Committee of Space Research of the International Council for Science, and he's also NASA Distinguished Scientific Achievement Medal. He's not wearing them all, but he's probably wearing them well. He's the founding editor of the journal I just mentioned, and he's also a fellow of many distinguished institutions. I won't list it, he's on there. So, what is space weather? Please welcome me and join me in welcoming Dr. Lanzerottti to tell us what space weather is. Thank you.
And ask what is some fundamental research that you might do to understand and to solve the very practical problem. And so that's the bottom line here. But in that bottom line is also the issue of this natural environment that we live in, whether it's the Earth's atmosphere, or whether it's a space environment above the Earth's atmosphere, or whether it's the sun, has all kinds of interesting properties to it that can affect our technologies. And as technologies develop, and new technologies develop, we have to understand new properties of the system that we're living in. And that also drives the fundamental research for understanding the system that we're living in. And so that's part of that whole thing. In addition, the engineering aspects are really, really very important. And they drive the science, and the science drives the engineering. And in order to make that point, I'm going to talk first about some history. I'm going to go over some history first here to show you how we progressed. And the history mostly has to do with communications, and I came from Bell Labs, and that was communications business over those years. But communications evolved from the very first time when Faraday understood somewhat electromagnetic induction was, and then the telegraph was established, and the telegraph then didn't lead to, but following the telegraph was radio communications, Marconi broadcasting across the Atlantic, and on to new kinds of telecommunications, also new technologies, such as electrifying various cities and the United States and the rest of the world. And now we are up, at the very end of my talk, I'll talk about GPS systems and cellular telephone systems and how we need to understand better our solar terrestrial environment, because these also are impacted by the weather out there between the sun and the earth and the weather in space. So I want to talk about history so you get some feel for why we are where we are today, and then we'll talk about today and the current situation that we have in terms of coupling science and engineering. So that's basically the title of this talk, and shaping the Earth's space environment. We'll have to talk about that a little bit. The Earth's space environment is very different than the Earth's neutral atmosphere, but we want to really talk about affecting life and technologies on Earth and in space. Back 50 years ago, at the time of Sputnik, back 50 years ago, this is what the world looked like. And as a matter of fact, oh, hang on. What did I do? I hit the wrong button here. Oh yeah, this middle button. This is taken from a physics textbook, 1956 physics textbook. This is just at the time of what was called the International Geophysical Year, 1956-57. This is taken from a textbook written by Shortley and Williams. It was a very famous physics textbook at that time. You remember that, Neil? Shortley and Williams. It was about this thick. It was about this thick. And I mean, this is a colored view of Shortley and Williams. It was black and white. But this is what the Earth's magnetic field was illustrated in Shortly and Williams, basically extending out into the solar system. And these are stars in the background, and here's the sun. But even at that time, we knew that this wasn't empty space because there was aurora going on here, and cosmic rays had been measured 50 years before at the beginning of the 20th century. But they weren't seen to be consequential in terms of technologies. And so Shortly and Williams illustrated the physics textbook like this. But here's the situation we have today. This is the situation we have today. Solar storms cut airplane radio contact. Morristown, New Jersey, near where I live. Solar flare may disrupt communications. Magnetic North Pole shifts, forces runway closes at Florida airports. This is January this year. January this year. We have up here, space weather could wreak havoc in gadget-driven world. Yahoo News, February 20th. No, that's only about 4 days ago. Solar storm could end up just a nuisance. That's about 11 years ago. Largest solar flare in 5 years, 1989 Korea. So these are what's going on out there. What's going on in weather and space that cause these kind of headlines that you see here. Italy blames disruption of contact NATO uses on strong solar activity. It's about 4 years ago. This is in Space News. Well, what we have is a very complicated situation out there. We're going to come back to this next slide in, 2 or 3 times here so we can talk about various details of it as we go along. But we really don't have this situation now. We really have this situation. This is what we've learned in the last 50 years about the Earth-space environment. We have the sun. We have, I keep forgetting the middle button is the one to push. We have the sun with all kinds of active regions on the sun. We have solar flares. We have things called coronal mass ejections where the sun is ejected out. Lauren Acton probably talked about those at his first talk. We have a solar photosphere here that's 600 degrees Kelvin. And we have a solar corona which is greater than 1,000,000 degrees Kelvin. With all apologies to you solar physicists here, we still don't understand how you can have a cold surface heating this hot surface of the corona to such temperatures. Why is that the case? Fundamental theoretical problem. And it's a theoretical and an experimental problem because this high temperature drives off all kinds of mass from the sun which can impact the Earth-space environment, which is way down here. And that magnetic field you saw on the first view graph is right down in here, extending out, but it doesn't extend out throughout the universe. As a matter of fact, the Earth looks like a comet. If you could see the Earth, it would look like a comet with a tail extending way down here, more than 1,000 Earth radii, perhaps 2,000 Earth radii. We really don't know. We have the Van Allen radiation belts here. We have the solar wind. The solar wind is composed of electrons and protons flying at about 400 kilometers per second. This whole environment are electrons, protons with a few helium atoms, a few oxygen atoms, but it's an ionized environment. Way down here around Earth, what we live in, what you're breathing now, is a neutral environment. The oxygen, the nitrogen is all the electrons and that are neutralizing the atoms. But out here, it's all an ionized environment called a plasma. And above the Earth, about 100 kilometers, is an ionosphere. We'll come back to that later on in the talk as we talk about some of the technologies that are impacted by the ionosphere. There's a shock wave in front of the Earth here, a magnetohydrodynamic shock wave, which is analogous in this ionized environment to the shock wave that's produced by a supersonic airplane flying through the Earth's neutral atmosphere. So this is the environment that we're living in. This is the environment that causes all the technological and engineering problems. So let's have some historical perspective here. And I really like some of this because it tells me, it has told me, and I started looking at this way back when I was at Bell Labs, it tells me we really have to be fairly humble at times about what we know about the environment and how new technologies can be affected by it. Let's look at the telegraph in the 1840s. The first paper, the first technical paper, was a paper written by the senior engineer for a telegraph for a railroad company in England. He wrote this in Philosophical Transactions in 1849 called On the Spontaneous Electrical Currents Observed in the Wires of the Electrical Telegraph. Now the physics behind this is a physics that is still operative and still affects technologies today. And we'll see that towards the end of my discussion here. Barlow wrote a very interesting paper here, and at this time, data were plotted in papers. Or not plotted, but data were listed in papers because the data were not very extensive. So Barlow plotted his data for 2 weeks. Here, this was a measurement on a galvanometer which measured the telegraph signal along the railroad lines. The railroads used telegraphs in order to tell them when the trains were coming, when the trains weren't coming. It was a very new development, the telegraph. Electricity and wires and things had only been around for 10 years or so. Samuel Morse was very instrumental in that in the United States. And here's a plot of 2 weeks of his data, which were in his paper, just the raw data, which we plotted up separately. These are 2 weeks of data here, separated by taking a weekend off. And this was a weekend, I confirm that. He worked reasonably at those days. The observations described were undertaken in consequence of certain spontaneous deflections having been noticed in the needles of the electric telegraph on the Midland Railroad, the erection of which was carried out under my superintendency as the company's engineer. And you see, these 2 weeks of data are quite different in terms of the intensity of the variations. He didn't understand that at all. But an interesting thing about these data is, if you look at it closely, there's a diurnal variation. Every day there's an up and down of the electrical currents. And that has to do with the up and down of the electrical current intensities in the Earth's ionosphere, which we'll talk about later. But he also made a very interesting observation. In every case which has come under my observation, the telegraph needles have been deflected whenever aurora has been visible, deflected in a sharp way. This conclusion by Barlow was under considerable challenge for about 50 or 60 years by very eminent engineers and scientists in Europe and in the United States. They didn't believe that the sun could couple to the Earth in a way that would cause Barlow and subsequent measurements on telegraph needles to be deflected. They just didn't believe it. I mean, the sun puts out sunlight. How could you couple the sun to the Earth? Well, there was also another conclusion along the same line, and also he wasn't believed. Richard Carrington was a solar physicist. He was the family of a brewer in England, had a fair amount of resources to him, and in his house in Reading, Surrey, south of London, he built an observatory where he measured sunspots. Sunspots were really a very important thing to be measured at the time. They still are. It's about the only long-term measure that we have the variability of the sun over the last 150 years. Carrington measured sunspots from 1853 to 1861. Rather thick book, somewhat like this, where he sketched out the sunspots and he described some of them in somewhat detail. Recent Life of Carrington was published in 2007. For those of you who are really interested, it's a fascinating book about Carrington, about the lack of respect that he felt he was getting from his peers in the English community, the fact that solar physics wasn't viewed so importantly by some of the astronomers in England. It's the situation we still have today. And his brewery background, and it didn't really, anyway. If you're really interested in science, it's a fascinating book. Well, what Carrington saw was that on plate 80 of his book in 1859, about the 31st of August of 1859, he saw a huge sunspot group, The observation of this very splendid group on September 1st, 1859, and that's right out here, has had some notoriety. He witnessed a singular outbreak of light which lasted about 5 minutes and moved sensibly over the contour of the spot. There is a sort of solar explosion called a white light flare, where the sun explodes in a sunspot where it's white light. And basically that's the first observation of a white light flare. So Carrington reported that in the technical literature. He also recorded it in his book here. And simultaneously with the occurrence of this were some other occurrences across the Earth, particularly in Europe and in North America, the New England area of North America on telegraph lines. But the juxtaposition, there was no internet at those days, so the juxtaposition of these occurrences didn't occur simultaneously. It took weeks and months and even years before people got together and put the two and two together. But what happened was there was a tremendous magnetic storm on Earth that resulted a magnetic disturbance, a change of the Earth's space environment. Must have been hit by the sun. Some of those emissions from the sun that I showed you, must have it was. And there was a large magnetic disturbance on Earth. And in fact, that disturbance resulted in arcing and sparking of telegraph keys and armatures from a wide range of stations, including eastern U.S., England, Scandinavia, Belgium, France, Switzerland, Württemberg, Austria, Tuscany. This is from a scientific paper in the 1860s. From the telegraph line from Boston to Portland, Maine on Friday, September 2nd, the operators continued to use the line without batteries for about 2 hours. When the Aurora, having subsided, the batteries were resumed. Published in 1860 by Prescott, who was a professor in Yale at the time. This wasn't really related to Carrington at that time, and when they were related, there was still this uncertainty about whether the sun could really do this. What's plotted here that you see is the Greenwich, England Observatory magnetic field variations, the north-south variation, the east-west variation, large excursions here over this time period. But this wasn't really related to Carrington's event either for quite some length of time. But it shows the large variations that could occur in the Earth's magnetic field measured by some sensitive instruments at that time. Similar variations were measured in Calcutta, India at that time. And the British having set up a magnetic measuring station there. And some of that data have been subsequently analyzed as well. Well, moving forward here now, about 60 years, 70 years or so, showing that people don't really remember, and also that the technologies have changed. Magnetic storm, a big magnetic disturbance, variations like we saw there recorded in Greenwich, England in 1859. March 24th, 1940, numerous problems. Transformer tripping, reactive power surges and other systems. Transformer tripping on Ontario Hydroelectric, 4 transformer banks in the Niagara district, 6 transformer banks in the Albany system. This was the first widespread effects on power distribution systems. So new technologies come along, the solar-terrestrial environment, the sun and the environment can affect the new technologies which are beginning the power distribution systems locally across North America and in Europe. We're starting to become much more sophisticated, somewhat more interconnected, but not like they are today. A large meeting by electric power companies and the telephone companies because they all observed similar effects. There were also widespread effects on radio and on landline telephoning. Here is a measurement of some data, the voltage excursions on the Minneapolis to Fargo telephone line with large excursions here, 200 plus or minus 250 volts or nearly 500 volts peak to peak during this local time when the power systems here in North America and in Canada went down. There was a large meetings convened to try to understand this solar terrestrial environment, how to protect both communication systems and now power systems. Now remember, this is 1940. We're going to jump forward here in a moment. This was outages in Canadian systems as well as U.S. systems. But people don't remember very well, and the sun goes through some cycling, as you'll see shortly. And so, come February 10th, 1859, what do we see? We see that at almost the exact moment when the magnetograph traces leaked and the aurora flared up, huge currents in the earth induced by heavenly turbulence manifested themselves not only power lines in Canada, but cables under the North Atlantic. Again, the Canadians were surprised, and so was the telephone company. Here's the power line, here's the telephone, here's the voltage on the cable system. I hope you on this side can follow because I can only have one of these pointers. It's okay? Okay, good. This big voltage excursion here completely knocked out voice communication across the Atlantic for the order of an hour or two here. And this very, very lyrical kinds of writing appeared in the New Yorker magazine. Not in some esoteric technical journal, but a report in the New Yorker magazine of 1959, not so long ago. Some of us were in high school at that time, maybe college, not so long ago. And circuit breakers began tripping out in Ontario transformer stations, plunging the Toronto area into a temporary darkness broken only by the strange light of the aurora overhead. Again, from the New Yorker. Yeah, I think that might be a good idea. Thank you very much. I didn't think I needed it, but I think maybe I do after all. Thank you. So, the Canadians here, 2 solar cycles later, basically 18 years, are surprised again, as are the American telephone company, which is AT&T, which is what I worked for 37 years, and where I have a pension from. Early wireless communication. So, now let's jump. So we've talked about 2 technologies here historically. We've talked about cables, and we've talked about power systems. Now let's talk about early wireless communications. It's also illustrative, it's really important. Wireless was really a way you could have communications cheaper, because you didn't need all that infrastructure of putting cables across the Atlantic and everywhere and all the repeaters. And you could also increase the bandwidth of your communication by having wireless communications. So Marconi in England, from Perth, Cornwall, Marconi and his assistants were launching kite-supported aerial from Signal Hill, St. John's, Newfoundland, to receive his signals. He was pretty forward-looking. Nobody thought that this would work because the curvature of the Earth, all the signals would just propagate away. But by golly, he saw a signal. But he also pointed out that times of bad fading on his wireless signals practically always coincided with the appearance of large sunspots and intense aurora borealis accompanied by magnetic storms. These are, this is important, the same periods when cables and landlines experience difficulties are thrown out of action. So even though one has gone to a new technology, one has gone to higher bandwidth in propagation, one has gone to a cheaper system, to some extent, one still is having a problem here with the solar-terrestrial system, and we still don't know what it is out there coupling the sun to the Earth, and what's causing all of this. There was a big study of wireless communications. AT&T instituted a large study in the first part of the 20th century here. Here's a plot of transatlantic signals versus sunspot numbers. So it's quite clear that the field intensity, the transatlantic signal strength changed with sunspot numbers. And these sunspot numbers were only the sunspot numbers and the transatlantic signal strength, so sort of yearly averages here. But it's obvious that the sun is influencing the transatlantic signal, but nobody understood quite why. An interesting observation at that time in 1928 was, here's 2 different frequencies across the Atlantic. One very, very low frequency, 60 kilohertz, and one at 18 megahertz, which is still a frequency that's used for high-frequency communications in some instances by the Defense Department and in the polar regions, for example. And here's a component of the magnetic field of the Earth, green here. When it changes here and decreases a fair amount, one of the signal strengths on the high frequency signal changes with it, decreases, and the transmission at very low frequencies continues. So obviously something's going on in the Earth's upper atmosphere that's causing this variation in signal. And this was important commercially, because as the New York Times reported in January 23rd, 1938, for a different event, violent magnetic storm disrupts shortwave radio communications. Transoceanic services transfer phone and other traffic to long wavelengths, that's this one here, as sunspot disturbance strikes. So one has to understand the solar-terrestrial system much better in order to understand this kind of variation, which affects your profit and loss. And obviously this is part of the research that was done, and AT&T continued this kind of research over the years. 1942 was a very interesting time. It was a very interesting time. The world was at war, and a new technology was introduced, the technology of radar, to look at bombers coming over the horizon into England and vice versa. Cables and telegraphs to power systems to radio to radar. Again, going back to our picture here, empty space. Empty space. This is what this is what the world still looked like. In 1956, 57, this was the world that existed when John Pierce at Bell Laboratories and Sir Arthur Clarke, 10 years prior, had proposed communication satellites. Arthur Clarke, just at the time of the Second World War, 1945-46, wrote an article in a more or less, it wasn't science fiction, but it was a popularized article on communications, on wireless communications, proposed geosynchronous spacecraft for broadcasting back to the Earth. Geosynchronous spacecraft sits at 6.6 Earth radii from the center of the Earth, and it's above the same spot on the Earth all the time. And that's what's basically used now for your satellite communications. The first communication satellite, operating communication satellite, geosynchronous, was SYNCOM-3, launched in 1963, about 20 years after Arthur Clarke's proposal. John Pierce at Bell Laboratories, about 1954-55, proposed low Earth orbiting spacecraft to do communications as well. And that resulted in the Telstar-1 being launched in 1962 into the Earth environment at low Earth orbit. But they had no idea that the Earth space environment here was not empty space, but could affect the operations of these spacecraft in very serious ways. And as a matter of fact, the Telstar-1 satellite failed after only about 8 months in orbit, due to the electrons and protons and the trapped Van Allen radiation belt. And of course, that's what happened. The American Explorer-1 satellite with Van Allen's instrument on it here. Here's Pickering, a JPL director, Werner von Braun down at Marshall Space Flight Center, and Jim Van Allen from the University of Iowa with the backup of the Explorer-1 spacecraft after Van Allen discovered the Van Allen radiation belts. Here's a description from one of the Russian papers on that, and Van Allen was featured on the cover of Time magazine. So the Earth was not an empty space environment in here at all, but as a matter of fact, it was that very complicated environment. So contemporarily, here's the sunspot cycle. Before we go on with some more practical technology, here's the sunspot cycle starting about 1800, the approximately 11-year sunspot cycle, quite variable across this time interval. And I've indicated here some of the time periods that we've just talked about historically. Here's Barlow's telegraph, here's Carrington's white light flare, here's Marconi at the time when he broadcast across the Atlantic, here's the first electrical power disturbance, here's the disturbance on radar, this is when Van Allen launched the spacecraft, and here's where we are today at solar minimum, which has lasted somewhat longer than people had predicted. And during this time, we've had a number of impacts on various technologies. Here's one having to do with radio, and they're pointed here to the time when these headlines occurred throughout the last 10 or 20 years or so. Scientists says CBS radio space sunspot interference, New York Times. Sunspots playing tricks with radio. NASA says solar flare caused radio blackouts. Utility system effects of space plasma. Blackout darkens Quebec. As a matter of fact, in 1989, and you'll see a subsequent picture here in a few moments, Quebec was completely blacked out by a solar event. The entire power system in Quebec, and nearly knocked out the power system in New York and New Jersey at that time. Solar flares, largest solar flare in 5 years, could break up communications from communication satellites. 2 Canadian spacecraft called Anik were completely disturbed and put out of commission here in about 1990 or so. NASA Orbital blamed Galaxy 15 failure on a solar storm, and we'll come back to that in a moment as well. It just happened in about 2010. And then solar storms could disrupt everything under the sun in U.S. to warn pregnant women on airline radiation risk, which it continues to be an issue in terms of airplanes flying into the polar caps and at some high altitudes. So as we saw, the sun puts out a variety of emissions. The sun puts out X-rays, all these electrons and protons, these coronal mass ejections, which are just much more high intensity electrons and protons, magnetic fields that are embedded in these electrons and protons, which can affect the Earth environment, so the solar wind, which we talked about, electrons and protons, solar radio noise, which can affect radars and ultimately GPS. And then we have cosmic rays coming into the solar system. So we're going to now look in more detail at this environment, in particular how the environment can affect some things. And what we're going to talk about first is the effects on space systems and effects on humans of the trapped radiation belts. And after that, we're going to go down and look at the ionosphere, how changes in the ionosphere can affect technologies as well. So the major space environmental hazards on a spacecraft, this is a robotic spacecraft, not a human-occupied spacecraft, are multifold, as you can see here. Here's the spacecraft, and these are illustratively shown here. I've adapted this from some work that the Aerospace Corporation has done, but we can just go around this. The solar power array can decrease due to radiation damage from the electrons and protons striking the solar array. In addition, the electrons and protons striking the solar array can cause discharges on the solar array. And this was an issue that we had with several AT&T spacecraft that I was involved with. And as a matter of fact, you'll see something here from, where was it from? CNN, I think. I'll show a headline, where we lost an AT&T spacecraft in 1997 or so, and I did a lot of analysis for that, just due to this solar arc discharge on a solar cell. Spacecraft components can become radioactive just because the electrons and protons striking. If you got the wrong materials, not the wrong materials, with some materials that are in the spacecraft component, they become radioactive. That's not so bad unless the spacecraft comes back, but it can be bad in some instances, affect electronics. Spacecraft has star sensors which orient them in space. If you have too intense, the star sensors are looking at the stars. Obviously, that's what they're called, and that's what, so you look at a specific star, you know where your spacecraft is oriented. However, if you have very intense electrons and protons, the star sensor can be either destroyed or have all kinds of interference in it from the electrons and protons hitting the star sensor. Surface materials on the spacecraft can be degraded from radiation. Here's before, here's after, as an illustration. And this is important because the surface material on the spacecraft keeps the spacecraft from getting too hot, from getting too cold. And there's very, very delicate thermal analysis and designs and materials and stuff for spacecraft. And if you degrade the materials, you're going to change the temperature characteristics of the spacecraft, change the temperature characteristics of the spacecraft, operates differently, or why not operate at all? The electronics can degrade due to total radiation dose that hit the electronics. Some electrons and protons are energetic enough that they can get inside the spacecraft, and they can what's called dielectric charging. The cables and things can charge up and then discharge, just like a lightning discharge on the surface behind shielding or deep inside. So you get an electromagnetic pulse, which can then cause interference in the electronics. Also, you can have effects in the microelectronics. You can change a bit, 1101 to a 0101, for example, and that changes the computer. It changes the computer, it changes the control system of your spacecraft. And this is just not academic. Italy blames disruption of COMSAT on strong solar activity. As a matter of fact, one of those things that we saw affected this. Orbital blames Galaxy 15 failure on a solar storm, and that was indeed the case. And this is the killer sun ejection killed TV satellite. This was the AT&T Stelstar 401 satellite, which was killed in 1997 by a solar event. This was a very interesting occurrence here, the Galaxy 15 failure. Galaxy 15's control system failed, and it continued broadcasting, but the satellite slowly drifted in orbit, and every communication satellite that it went past, it interfered with the communications. And so it was there was no way of controlling it. Finally, it got to some location, and they kept sending signals, and the signals didn't get recorded, and one thing and another. But after a year, Intelsat recovered Galaxy 15 to test location. They did recover it, finally. Turned it off, and are moving it back now to where it should be. But it interfered with quite a few communication satellites that were up there, and the ones it was interfering with, they had to change signals to another communication satellite so that they could come back, so they weren't interfering It was quite a situation over the last year or so. Well, because of the space radiation issue, NASA, because a portion of NASA's program has been developed into something called Living with a Star. And over the next couple of years, NASA will be launching in 2012, NASA is going to be launching 2 spacecraft to measure in much more detail the Earth's radiation belt environment than we have had measurements of for the last almost 30 years. The models of the Van Allen radiation belts, even though they've been known to exist for 50 years or so, the models are very rudimentary, very rudimentary. And so it's hoped with these 2 spacecraft called the Radiation Belt Storm Probe that the models can be greatly improved so that the design of new spacecraft can be greatly improved, and so that the operations of operating spacecraft within that environment that's going to be measured can be greatly improved as well. But space radiation is not just for robotic spacecraft, it's also for astronaut safety. Here, this is a cover from one of the Space Weather Quarterlies of a couple of years ago or so, which was devoted to radiation hazards. And here's a plot that Ronald Turner from Answer Corporation plotted the effective dose of astronauts over calendar years since the launch of astronauts and various orbits that they have, low Earth orbit. Here's deep space, that means astronauts going to the moon. These are all the astronauts who went to the moon. And these are basically space station astronauts and the radiation doses they receive. And these radiation doses vary by a fair amount, depending upon the intensity of the radiation belts and the intensity of solar activity that accompanies the mission or that was just prior to the mission. And so this radiation issue is really an important one for astronaut safety. Radiation is also important for airline passenger safety, as we indicated earlier on. Tests of cockpit radiation show levels above a federal standard. This was a few years ago in the New York Times. And again, this is that headline about pregnant women on airline radiation risk. This was 1990, 20 years ago. But it still is an important issue, particularly now, and we'll come back to this again in terms of communications over the polar cap, but particularly now with airlines flying over the polar caps, now since the Cold War, we can go over the Far East directly from Washington, from Houston, from Newark, New Jersey. A very interesting event occurred in a Qantas flight across North America. In 2003, there was a very large solar event that occurred in 2003. And here, this plot that I plotted here is the radiation level in the Qantas flight as a function of time from Los Angeles to New York. Here's the plot here, Los Angeles to New York. Can you see over here? Okay, this is Los Angeles to New York, and this is the route here, and this is New York back to Los Angeles, this route here. Now, it turns out that this Qantas pilot is a very interesting guy. He has a PhD in physics. Has a PhD in physics, and his PhD was acquired basically by doing radiation measurements in the flights that he was making around the world. He's also a vice president of the International Airline Pilots Association, which is a quasi-union. But so he's very interested in this in terms of pilot safety, in terms of passenger safety, and he's quite an interesting fellow. Quite an interesting fellow. But he had one of his radiation monitors on this flight, and what he found was after getting partway to New York, all of a sudden there was a factor of 2 practically increase in the radiation level going across the United States. And this factor of 2 increase in the radiation level was the solar event that occurred on 2003, penetrating all the way down to airline altitude, increasing the dosage on that flight by a factor of 2 or so. And then they landed in New York before the event was over, so he doesn't know how long it lasted here. One could look at other data that were measured, and one can get an idea of that. But this was the first measurement on an airplane of a solar particle event that was seen at airline altitude, and he published this in the Space Weather Journal. And as I said, he has a PhD in physics, and he's gotten it by this. He's also has a little company where they've been selling radiation devices to fly on airplanes around the world on various things, and he's still doing this as a Qantas pilot. Now let's talk about channels here briefly. We have the sun here. The sun has all these emissions, which we were talking about, including sunlight. And sun can ionizes the upper atmosphere at about 100 kilometers or so. And there's various layers to the atmosphere. This is historical nomenclature. They're really not precise here, but there's something called the D layer, the E layer, the F layer. It's really this E layer here at about 100 kilometers that reflects Marconi's waves, that reflects the high frequency waves around for radio communications. And on the night side, there still is an E region and an F region that exists, and over the polar regions. And there's scientific investigations of these even to today to understand the persistence of this ionosphere and its various characteristics, as we'll see in a few moments or so. The emissions of the sun. The emissions of the sun are various types. It might be hard to see this, but this is 100 kilometers here, this E region, and various emissions from the sun, extreme ultraviolet, solar particles, produce this ionization that is seen here. So if one has variations in these solar emissions, including solar particles, one can get variations in this ionosphere, which is what is producing a lot of the effects that we have talked about prior to now. So, ionospheric variations can cause induction of electrical currents in the Earth, from the telegraph lines to the power lines, power distribution systems, long communication cables, and pipelines, which is very important in Canada, which lies under the auroral zone. And the physics of that can be summarized in three sentences here. It's much more complicated. But what one has, basically, is time-varying electrical currents in the ionosphere. In this ionosphere, time-varying currents are caused by changes in the solar output of various types, including the coronal mass ejections, the solar wind, and all. These time-variation electrical currents in the ionosphere produce time-varying magnetic fields at Earth's surface. And finally, the time variation of the Earth's field at the Earth's surface produce electrical currents flowing in the Earth. And those electrical currents flowing in the Earth are what produced the effects that Barlow saw 160 years ago. The electrical currents flowing in the Earth tried to find the best conductor they can find in order to flow through. The Earth is not a tremendously good conductor, but if you put a cable on there and you ground it at a couple of places, or a power system, that's a really good conductor. And so these currents are going to flow through this conductor, and they're going to cause all kinds of havoc on the systems that are connected to the conductor. And that's what exactly happened in 1989 when the power system in Quebec went down for about 12 hours or so. As a matter of fact, the power system in Quebec went down, so New York State wasn't getting power from Quebec. So New York State asked New Jersey for power. New Jersey asked Ohio and Maryland for power. And there was too much power being sucked through New Jersey, and an electrical distribution transformer, several of them as a matter of fact, and this one was at a nuclear power station in southern New Jersey, blew down because of the superstorm in March '89 that took out the Quebec power grid in 90 seconds and was down for the order of 12 to 14 hours or so. So there were several of these transformers that were destroyed because of this Quebec situation. Now, other transformers have been destroyed through lesser disturbances as well. As a matter of fact, this has become a much more interesting issue because of the prevalence now of these kinds of transformers, because of the prevalence of the interconnection of electrical grid systems across the United States. Texas is isolated, I believe, from the rest of the country, but in terms of electrical systems, I believe that's the case. When we had this situation in New Mexico, I think Texas was isolated. But the grid system, other than Texas, is really pretty much connected, particularly in the eastern part of the United States. So when you have a power outage in New York because some tree came down, they're all interconnected back to Ohio and Indiana. And so this kind of situation can be really serious. And in Europe, it's the same thing. And so there's been some scholarly work begun to look at this. And here was a paper published in Space Weather back in 2004. There's been a couple of ascents. Space Weather and the Electricity Market, an initial assessment. by a chap at the Catholic University of America and a chap at the Goddard Space Flight Center, where they looked at some of the economic as well as engineering and scientific aspects of this. This chap at the Catholic University is an economist, and he's an economist who looks at utility system economics. It's a very interesting paper, both from the point of view of the economic analysis and the statistics that went into it. And there's a fair amount of scholarly work now going on like this, both in the universities as well as in the utility companies. So, ionospheric variations can also affect wireless signal reception, propagation, attenuation, GPS, interference, scintillation. So what we have here at the ionosphere, Marconi's waves bouncing around, some pop out, some bounce around, long wave, short wave. So you change this, you're going to have changes in your communication system. And what we know now is that the ionosphere can be very variable. And the ionosphere can also have what's called plasma bubbles and irregularities. There are clumps of electrons and protons that somehow gather together in locations that are unknown why they occur. And when you have these plasma bubbles, they can cause exceedingly strong influences on communication signals that pass through them to a ground-based antenna. They can also affect, in very serious ways, radio reflection and all. And the solar radio burst from the radio can also affect, as we saw with the radar. And that's very important for transpolar airplane flights, for example. Here's the United Airlines polar routes in 2005. So every airline in 2005 had about the same number of polar routes: Continental, United, and several of the Far East airlines in Japan and Taiwan and China. And these airline routes now have probably doubled, if not more, across the North Pole. 2003, 30th of October is again that event. The AP reported the airlines flying north of the 57th parallel experienced some disruptions in high-frequency radio communications due to the geomagnetic storm from solar flares. As a matter of fact, some of the airlines had to divert their routes from this and land in Anchorage here before they went on. And there are disruptions to the passengers, disruptions to connecting flights, and a fairly large increase of cost to the airlines in having to change the routing. As a matter of fact, during a January 2005 solar event, which really wasn't very strong, but just as an illustrative example, the total cost impact was to United Airlines was the order of $250,000 for just that one time. So you add that up several times a year during solar maximum, that becomes big dollars. $1 million here, $1 million there is a profit impact on the airline for diversion and for passenger frustration, as a matter of fact. So one has to worry about solar events over the polar cap, and we haven't said anything at all here, of course, about the increased radiation to airline passengers, and that is factored into the airline operations back in the States when they plan out the next day's route, the next week's route. They have to take into account, they try to predict, they try to use data that exists from NASA and from NOAA to understand whether there will be solar particles and enhanced radiation over the pole. To do airline traffic control using GPS signals on airlines and land airliners, vertical landing approach to 250 feet. And at two instances here, there was zero coverage across the United States. You could not do air traffic control using GPS during a fairly large amount of time here in two separate instances here in November and December of 2003 towards the end of that year. So the wide area augmentation system is still under development, but the changes in the ionosphere that affect this air traffic control is something that has to be taken into account, and is trying to be taken into account, trying to be understood, but it's not understood well enough yet at all. And related to that, and related to solar noise, and we're getting to the end because this is nearly the most modern technology that we have in the GPS system. There was a large solar event in December 2006 also one in December 2005, which occurred similarly to this. This is a picture of the sun taken a couple of days after the solar event, and this sunspot had moved. It was back about here. The sun's rotating, but this is the only picture that exists at that time. A paper here published by some chaps from Cornell University, The Effect of the Intense December 2006 Solar Radio Burst on GPS Receivers. Here is a plot of the GPS receivers in Alaska, part of southern Canada, and across the United States. And at this time, the yellow here are all of these receivers were receiving some data through the World Wide Web from these GPS receivers. The red ones were completely blanked out by this solar event. And if you take these data and then you look at the airline wide area augmentation system and where an airline can be affected, or a ship docking, for example, you get a plot like this. This is a brief loss of vertical guided approach here in red, and pink is less impacted. But here's the continental United States. You see Texas down here in Florida. There's the white WASP coverage and availability of vertical guided approach service on 6 December completely wiped out across most of the United States from this solar radio event. Lasted for about 10 or 15 minutes. So if we'd had this implemented at that time without any mitigation, and we still don't have mitigation, if we had this implemented, there would be no air traffic control for about 10-15 minutes across the United States, which is not a wise thing, particularly if you're trying to land under a total GPS. I'm not saying that this is the final word by any means, but what this points out is a very practical, getting back to my first words here this evening, a very practical need in terms of operations, pointing out some real serious science that we need to do to understand in order to implement this kind of technology. So in summary, we've talked about cosmic rays, solar X-rays, solar radio, particles, magnetic field, radio, a whole slew of things, including the Earth's conductivity for these currents that flow in the Earth. There's a wide range of science topics here, amazing, from cosmic rays to the Earth's to the construction of the Earth. Really fundamental science and all of these things that are affecting our modern day technologies. And in fact, it can be summarized here, solar effects produced at Earth. Just a few days ago, 4 days ago, Jane Lubachenko, the administrator of the National Oceanic and Atmospheric Administration, which has responsibility in the United States for much government-supported, government-provided prediction services and space weather, Jane said at the AAAS meeting in Washington, it is not a matter of if, it's simply a matter of when and how big the disturbances of the sun are on Earth and its technologies. So here we are. We started out 160 years ago from this to this, where we have all these technologies now that are impacted by the solar terrestrial environment that we live in, by the space weather that we live under, that is affecting everything from our spacecraft, to astronauts, to solar cells, to passenger radiation, radio waves, cellular, electric grid, GPS, telecommunication systems under the Earth, radar, everything. Thank you very much.
Anybody some questions?
What is known about the effects of this kind of radiation on passengers and pilots and aircraft?
I think the passenger situation is not an issue because they're very sensitive to the possibility of solar particles, and they do reroute planes during those times. With regard to the crew, they're monitoring crew health and safety and the radiation. Not as much in the United States as is done in Europe. And I don't want to get into that because it begins getting into union kinds of issues. The Europeans have been stronger in terms of radiation monitoring of crew than the United States. Any other questions? Yes, sir.
I'll say something about the atmospheric currents. Are they DC, AC, do they horizontal, vertical, what frequency ranges? Just trying to get some rough idea of what's going on there.
Everything in the Well, they're not DC current. I mean, the ionospheric currents are always changing with time. They're always changing with time, and they vary. They vary from a few seconds to. But the scale size, the scale size in terms of spatial scale varies depending upon the frequency of the change. So if you have a change that's occurring over say 100 kilometers, those are very slow, but those slow changes may penetrate deep into the Earth. These fast changes of the order of a second, or 10 seconds or so, are very small scale changes. They don't penetrate very deep into the Earth.
So it's called sub-hertz.
Yeah, they're sub-hertz, basically, yes. Yes, sir.
What is being done to improve the lessons of the power grids and the systems to avoid the catastrophes that happen in that?
There's a fair amount of work at the Electric Power Research Institute in Menlo Park, California on this. There are some possibilities of introducing capacitor coupling between you use a capacitor to separate the ground from some of the transformer things. But it's costly. Utilities don't necessarily want them to be put in. And there's also some issues about how effective those are. It's a big issue. There was the Parliament in the UK convened a meeting back last fall where they looked at just this question, whether some of these mitigation procedures of a capacitive coupling could be introduced in the UK system. And there's going to be another meeting similar to that convened by several Congress people in the United States on April 11th, I believe, where they're looking at that in more detail. But nothing has been really put into place. It's basically just engineering studies to this point. And they've been going on for about 20 years, these engineering studies. No value judgment made by that, but that's a comment. Partly it's because these things do vary with sunspot cycle. So you can have a big solar disturbance at solar minimum, but it might not be quite as probable. During solar maximum, you see more. I used to say at Bell Labs that our CEO changed every 4, 5, 6 years, and so he forgot what had happened, 2 solar cycles ago. And that's the same way in the power industry, as a matter of fact. So if you don't have a problem for 4 or 5 years, then you forget, and your CEO forgets. So he comes in and you try to tell the CEO, well, we've got to do something about this, or you tell the CEO's underling, but they've forgotten about it. That's not a problem. We haven't seen any problem in 4 or 5 years, so we don't have to worry about it. I'm sorry to get off on this, but I had to fight that for a long time. Several solar cycles, as a matter of fact.
What's the current situation with regard to early warning of solar storms? And what do we have going, and what's the plan to improve that?
That's been improved a fair amount in the United States with NOAA over the last few years. It's not ideal, but NOAA has become has improved in terms of their funding level, in terms of looking at this issue. But there's some really fundamental science issue, which I didn't go into here. Some of these events can be seen 2 or 3 days ahead of time, propagate the time from the Earth. I'm sorry, I missed that one. The time to propagate from the sun to the Earth is of the order of a couple of days. And so one can do some prediction, as Professor Lane has suggested here. But not everything can be predicted, because this solar radio burst that knocked out GPS just a couple of years ago that I pointed out here, the solar radio burst occurred at the same time as the big solar flare. Well, that takes 8 minutes to get to the Earth. So it gets to the Earth at the same time you see that there was a flare. Driven by the need to understand when an X-ray or when a solar radio burst is going to hit Earth. And we need that a day ahead of time. And it affects cellular phones. When I was still at Bell Labs, AT&T, we were looking at cell sites because they are affected the same way that the GPS are. Same way. If you have an outage of your cell phone sometimes, it can be a solar effect.
Yeah, I would say there's no way to predict them, at least until my proposal has been reviewed. It's an important part.
It is really a fundamental problem driven by fundamental physics, but it's also driven by the need to understand for practical purposes. So I wrote an editorial for the Space Weather Journal a year or so ago where I said that this is a problem that really hasn't been looked at serious enough and hard enough, and it's really really an important scientific issue. Yes, sir.
The implementation of the flight control system that actually next gen, I think is all GPS based. Are they, and I think it's supposed to be rolled out next year. I don't know if you're familiar with that.
Yeah.
Are they taking any sort of precautions?
Yes.
They're phasing out VOR.
Excuse me?
They're phasing out all the other redundancy systems that they've used thus far.
Is everything going to be phased out? If everything is phased out, I think there's some concern. I think they're going to continue some of it during this time. If one used dual frequency GPS, one improves the system quite a lot. But there's still some of these uncertainties that really need to be worked at really seriously.
We're working our way back to, well, we're not doing it, the sun's doing it, it's working its way back to the maximum. So there's going to be a lot more of these storms over the course of the night. You saw in the news maybe last week or so, the first big storm since, in this cycle. And it's just going to be just